weighted residual method if we assume the trial function as a polynomial function. Previous video we have discussed if we assume the trial function as a trigonometric functions where we assume our trial function as a sine pi x by L, and then we assume that weight function. So in the Glerkin weighted residual method, we know that trial functions and the weight functions are same. Okay, so here you can see we assume our weight function as sine pi x by L. Basically it is very similar. Okay, you can assume a sine pi x by L, but here we just assume sine pi x by L, and then we operate the weight function on the residue and we make it 0. We find A, we find the value unknown values, and we try to plot our approximate solution, and that actual solution we observe that we get some acceptable result. Okay, so here we just assume our trial function as a trigonometric function. Now if we assume our approximate solution as our approximate solution as our approximate solution as our our polynomial function. Okay, if we assume our approximate solution as a polynomial function, here also you can see that we are solving the same problem. We are solving the same beam problem, simply solid beam, and we have moment acting there, and we have our moment equation ei d2y by dx2 minus m0 that equals 0. Okay, so what we'll do, we'll assume the trial function, okay, as a polynomial, and we'll apply the boundary condition. See, already have discussed the weighted residual method. You can assume any trial function, but the trial function must satisfy the boundary condition that original function was satisfying. Here our trial functions basically like this, and if you consider, if you see our original solution, and if you observe that our original solution satisfying the boundary condition at y is equal to 0, at x is equal to 0, and y is equal to 0 at x is equal to L. Okay, so this same boundary condition our trial function must satisfy. Okay, so our trial function we assume like this. We assume our trial function as a polynomial like a plus bx plus c x square. Okay, now what we'll do, we'll put our boundary condition. Okay, we know that x is equal to 0, our trial function should be 0. So if you put it, then we will get a is equal to 0. So here we get a is equal to 0. Now again, if you put our second boundary condition that at x is equal to L, our value of y is equal to 0, that means our trial function value also should be 0. Okay, so at 0 at x is equal to L. Okay, now if you put that value, what we will get? We will get b is equal to minus CL. Okay, now if we put the value of a, b, and c. Okay, if you put the value of a and b and the c, we will get our trial function as we will get our trial function as minus CLX plus CX square. Okay, now if we take the common term c and x, if you take minus c common term, then we will get our solution as CX, okay, in bracket x minus L. So this is our trial function. Okay, so our trial function basically look like this. Okay, Cx in bracket x minus L. Okay, it is very similar in nature that we already obtained in our trigonometric function. In that we obtained our trigonometric function as our a sine pi by xl. We assume we use that u trial function as a sine pi x by L. Okay, and then we have written that is our C1. We have written here as a C1 N1. Here also we are writing that u as a C1 A1, C1 basically a C, and N1 basically x in bracket x minus L. So this is our trial function. Okay, now what we'll do, we'll again take the double derivative of that u, and we'll put the value of the double derivative. So here you can write d2u dx2. Okay, here ei term will come minus m0. Again that value will not be 0. Okay, because we assume u instead of y. Y is our actual solution, actual value, but instead of y we assume as u. So this value will not be 0. Okay, so obviously this is our residue. Now what we'll do, we get the residue. Okay, we get the residue. So our residue is coming like this. Our residue is coming like this, EI into 2C. Okay, EI into 2C minus M0. That is our residue. Okay. Now again, we know for Galerkin weight residual technique, we assume that trial function same as, we assume the weight function same as our trial function. Okay. So here again, we are assuming our trial function similar to our, we assume our weight function similar to our trial function. So our trial function was C1 N1. Okay. Again, we are just deleting, we are not considering the constant term, we are assuming that variable term x in x minus L. So this is our weight function. Okay. Now again, we obtain our residue and weight function. Now what we'll do? What we will do? We'll basically operate that weight function to the error and we'll make that value 0 in average sense over the entire domain. Okay, and we try to find our unknown values. Okay, so what we are doing here, we are making our our error, or we are making the residue 0 in average sense over the entire domain. Okay, so we are operating weight function to the error and we are making it 0 in average sense over the entire domain. So we are doing the integration here. Okay, if you do the integration, if you make it 0, here you just do the one correction in this. This value error is here, basically error is at EI2C. Okay, so what you have to do, you have to write EI2C, EI basically 2EIC, that value like this. Okay, this is the error. Basically this error will come here. Okay, this error will come here, and we have that weight function here N1, and that is our weight function. So if we operate the weight function on the residue and make it 0 in average sense, okay, we will get that value. We will get the value of one unknown, that C. C value will be M0 by 2 EI. Okay, you also can solve by yourself and you see whether you are getting the same solution or not. Okay, so here this error will be here. Okay, you do the correction here. So we get the value of C, that is equal to M0 to M0 by 2 EI. We get the value of C as M0 by 2 EI. Okay, so we already assume our approximate solution. We already assume our approximate solution. Our approximate solution as is your C, okay, x in bracket x minus L, and we know the value of C, so that value will be M0 by 2 EI, M0 by 2 EI into x minus L. Okay, so now here you can see we are getting the same solution. Okay, we are getting the trial solution or approximate solution same as our original solution. Okay, so here you just see we get our approximate solution and our actual solution, both are same. Okay, so previously you obtained this graph, basically you obtained using trial function as a sine pi x by L. Okay, so there is some error, but here you can see we get the same value. So our both the graph will overlap with each other. Okay, if you plot it, it will overlap with each other. So here you can see that if we use a polynomial function, then we can get our exact solution. Okay, we can get the approximate solution as a same as exact solution. Okay, I hope you get some idea. And again, it's not always the same, or it is not always true that if you assume polynomial function, then always you will get that exact solution. Okay, will not get our approximate solution as the exact solution. It is not always true. Okay, it is not always true that if we assume a polynomial function, then our approximate solution will be same as actual solution. This is not true. Okay, in some cases it may observe that though we are considering higher order polynomial, okay, higher order in the sense C0 plus C1x plus C2 x squared plus C3 xq, like that. If you consider higher order polynomial also, then also you are not getting the same as our original solution. Okay, so we have two options. In that case, we have to assume our different trial functions. Okay, you can assume that time you can assume some trigonometric function that we have discussed in the last video. Okay, so in that way basically we can solve in a Galerkin weighted residual method. Okay, so what we did, let me summarize. We initially assume a trial function. Okay, since we are discussing Galerkin weighted residual method, in that case our weight function also look like our weight function also look like similar to our trial function. Okay, so here we assume that weight function. Okay, and also assume one trial function, and once we assume trial function we try to find the residue. Okay, we try to find the residue, and once we know the weight function and once we know the residue, we operate the weight function on the residue and try to make the value 0 in average sense over the entire domain. So we do the integration over the entire domain. Okay, we make the integration over the entire domain, so 0 to L for this beam problem. Okay, and then if we make it 0, if we make that 0, whatever the unknown value is there, we try to find the unknown value. Okay, and once we find the unknown value and we will put the unknown value in our trial solution, we can get our solution, approximate solution. Okay, so one hand we have approximate solution, other hand we have our actual solution. You can plot it. Okay, in this method what you observe that our approximate solution and our actual solution both are same. So if you plot it, it will overlap with each other. Okay, I hope you got some idea. Thank you.